Welcome folks, welcome to a lecture on digital filter design. We have already seen that there are two types of filters. One is an analog filter, other is the digital filter. So if you really see, the analog filter and digital filter have some differences. The analog filter processes analog inputs and generates analog outputs, whereas the digital filter processes and generates digital data. The analog filters are constructed from active or passive electronic components, whereas the digital filter consists of elements like adders, multipliers, and delay units. Analog filter is described by differential equation, whereas a digital filter is described by a difference equation. The frequency response of an analog filter can be modified by changing the components. The frequency response of a digital filter can be changed by changing the filter coefficients. So if you really look at an infinite impulse response filter, the transfer function is given by h of z is equal to summation k is equal to 0 to m bkz raised to power minus k divided by 1 plus summation k is equal to 1 to n akz raised to power minus k. We have generally four types of filters in our syllabus. They are low pass filter, high pass filter, band pass filter, and band reject filter. If you really see the ideal characteristics of the filters, I am showing a low pass filter, a high pass filter, a band pass filter, and a band stop filter. These are characterized by a sharp cutoff. It is in general very difficult to make an ideal filter. So what we will see is, we will also see the responses of what is called as a practical filter. So the ones shown in black are the responses, equivalent responses for a practical filter. So let us look at a low pass filter. A low pass filter, the magnitude response is given as shown, and what you have is omega on the x axis and absolute value of h of j omega on the y axis, and the response actually goes from 1 and it tapers down slowly because that's a practical filter. But supposing you want to look at an ideal filter, this is shown by a dotted line, and the place where the magnitude goes from 1 to 0.707 of the max value is called as the cutoff frequency. So you are able to see the pass band and the stop band of the filter. Likewise, if you want to see a high pass filter has frequency response the way it is shown, and the dotted one is an ideal high pass filter, whereas the one with the sloping line is a practical high pass filter. The place where the response goes from 1 to 0.707 of the maximum value is called as the cutoff frequency. Likewise, we are showing the response, the ideal response of a band pass filter and the practical response of a band pass filter, followed by the ideal response of a band reject filter, as well as the practical response of a band reject filter. So how do you design digital filters? When you design digital filters, the step is first you design an analog filter. So what it means is, map the desired filter specifications into those of an equivalent analog filter, derive the analog transfer function. From the transfer function of the analog filter, obtain the digital filter transfer function. So what you do is, you always start with digital filter specifications. From the digital filter specifications, you make an analog filter specifications, and from the analog filter specifications, you design the analog filter transfer function, and from there you design a digital filter. So whenever we are looking at filter design, we are going to be looking at two equivalent diagrams. One is with one type of omega, and the other one is with the other type of omega. The one on the left, the specifications which are shown on the left, correspond to a analog filter, and the specifications on the right corresponds to a digital filter. So there are generally two types of analog filters. One is a Butterworth filter, the other one is a Chebyshev filter. The response of an analog Butterworth filter is given by h of j omega 1 upon 1 plus omega by omega c. Observe the type of omega which is being used here. because this is the one which corresponds to an analog filter, so it is 1 upon 1 plus omega by omega c o raised to power 2n whole raised to power 1 by 2. So if you really see, the passband is maximally flat. If you really see the response of a Butterworth filter, what you will see is, for different values of n, you get different curves for the Butterworth filter, and you get a not so sharp cutoff when n is equal to 2, and as n goes from 2 to 4 to 4 to 8, the response becomes sharper. So this is the type of diagram which is shown in your book. Whenever you have something like the order of the filter, you can obtain the poles for the filter by using an equation phi k is equal to pi by 2, 2k minus 1 into pi by 2n. Let us take an example of this for n is equal to 3. So if you really put n is equal to 3 in phi k is equal to pi by 2 plus 2k minus 1 into pi by 2n, you are going to get three angles, 120 degrees, 180 degrees and 240 degrees. Now if you take sine of 120 and cos of 120, you can actually get minus 0.5 plus j 0.866 minus 1 plus j 0 minus 0.5 plus minus j 0.866. If you really take this into the transfer function of the filter, you are going to get h of s is equal to 1 upon s plus 1 into s square plus s plus 1. What you will find is, when n is equal to 3, the roots will lie on a circle. Whenever you have a Butterworth filter, the poles always lie on a circle, so they are symmetrical about each other. And likewise, if n is equal to 2, you can obtain phi k is equal to pi by 2 plus 2k minus 1 into pi by 2n, and what you are going to get is two angles, 135 and 225. So if you take cos of 135, it will be minus 0.7071, and if you take sine of 135, it will be plus 0.7071. Likewise, if you take cos of 225, it will be minus 0.7071, and sine of 225 will be minus 0.7071 j. If you take the pole response of both the things, you are going to get s square plus square root of 2s plus 1. Likewise, when n is equal to 1 or 2 or 3 or 4 or 5 or 6 or 7, you can obtain the denominator of the analog transfer function. Shown is a diagram of a Butterworth filter with analog frequency on the x-axis and magnitude of h of j omega on the y-axis. If you can see that the response gradually degrades from 1 and it goes down. The place where it goes to 1 upon 1 plus epsilon square under the root is called as alpha p, and the place where it goes to 1 upon 1 plus lambda square under the root is called as alpha s. And you can see the corresponding pass bands and the transition bands of the filter. We have already derived the equation for the order of the filter, which says that n is greater than or equal to log of square root of 10 raised to the power 0.1 alpha s minus 1, 10 raised to the power 0.1 alpha p minus 1 divided by log of omega s by omega p. Let us do an example here. Determine the order of a low-pass Butterworth filter that has a 3 dB attenuation at 500 Hz and an attenuation of 40 dB at 1000 Hz. From the data, you can find out that alpha p is equal to 3 dB and alpha s is equal to 40 dB. Omega p is equal to 2 into pi into 500, which is 1000 radians per second. Alpha s is equal to 2 into pi into 1000, which is equal to 2000 pi radians per second. Therefore, the order of the filter is n is greater than or equal to log of square root of 10 raised to the power 0.1 alpha s minus 1 by 10 raised to the power 0.1 alpha p minus 1 divided by log of omega s by omega p. So here alpha s is 40 dB. So 0.1 alpha s will be 4 and 0.1 alpha p will be 0.3. So what you are going to get is log of square root of 10 raised to power 4 minus 1, 10 raised to power 0.3 minus 1 divided by log of 2000 pi by 1000 pi. So this comes out to be around 6.6. The order of the filter cannot be a fraction, so we round it off to the next highest integer to get n is equal to 7. So given here is the equation for the analog Butterworth filter, and we need to prove that omega c is equal to omega p by 10 raised to power 0.1 alpha p minus 1 raised to power 1 by 2n, which is equal to omega s 10 raised to power 0.1 alpha s minus 1 by 2n. We also know that one of the other equations for a Butterworth filter is given by absolute value of h of j omega whole square is equal to 1 upon 1 plus epsilon square omega by omega p raised to power 2n. So 1 upon 1 plus omega by omega c raised to power 2n is equal to 1 upon 1 plus epsilon square omega by omega p raised to power 2n. So we can derive the equation omega by omega c, omega p by omega c raised to power 2n is equal to 10 raised to power 0.1 alpha p minus 1, or omega c is equal to omega p by epsilon raised to power 1 by n. It can also be proved that omega s by omega p raised to power 2n is equal to 10 raised to power 0.1 alpha s minus 1 divided by 10 raised to power 0.1 alpha p minus 1. Hence, you can prove that omega c is equal to omega p 10 raised to power 0.1 alpha p minus 1 raised to power 1 by 2n, which is equal to omega s 10 raised to power 0.1 alpha s minus 1 raised to power 1 by 2n. So how do you design a Butterworth filter? Point number 1, from the given specifications of the filter, find the order of the filter, round it off to the next highest integer value, find the transfer function for omega c is equal to 1 radians per second. Now calculate the value of the cutoff frequency. Find the transfer function HAFS for the above omega c by substituting s by omega c. Omega c can be found out by omega p 10 raised to power 0.1 alpha p minus 1 raised by 1 by 2n, which is equal to omega s 10 raised to power 0.1 alpha s minus 1 raised to power 1 by 2n. So let us take another example. Design an analog Butterworth filter that has a 2 dB passband attenuation at a frequency of 20 radians per second and at least 10 dB stopband frequency at 30 radians per second. Given alpha p is equal to 2 dB and omega p is equal to 20 radians per second and alpha s is equal to 10 dB and omega s is equal to 30 radians per second, we make use of the formula n is greater than equal to log of square root of 10 raised to power 0.1 alpha s minus 1, 10 raised to power 0.1 alpha p minus 1 log of omega s by omega p. If you substitute the appropriate values, you are going to get n is 3.37 and you need to round it off to a value of 4. Shown here is a calculation of the transfer function for n is equal to 4. For n is equal to 4, you again use phi k is equal to pi by 2 plus 2k minus 1 into pi by 2n, where k is equal to 1, 2 and so on up to n, and you are going to get the angles 112.5 degrees, 157.5 degrees, 202.5 degrees, 247.5 degrees. To take sine of, take first cos of 112.5, it will be minus 0.3827, then take sine of 112.5, which is 0.9239. Likewise, you obtain all the poles, and from the poles you can obtain the transfer function of the analog filter. Once the Butterworth filters are done, we look at Chebyshev filters. There are two types of Chebyshev filters, Chebyshev type 1 filters and Chebyshev type 2 filters. Chebyshev type 1 filters are all pole filters, and Chebyshev type 2 filters have both poles and zeros. Chebyshev type 1 filters exhibit equiripple behavior in the passband and are monotonic in the stop band. So you can see the equiripple here, and in the Chebyshev type 2 filters you have monotonic behavior in the passband and the equiripple in the stop band. The magnitude response